तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we considered Y feedback and we saw how we could obtain a current controlled voltage source near ideal using that. Today, we will see an example on the Y feedback. The transistor feedback amplifier, this is only a signal picture, has the transistor with beta equal to 200 operating at 0.5 emitter current milliamperes. Determine the loop gain, forward transfer parameter, input resistance and output resistance. So, what it means is that we have to identify the feedback and determine the proper loop gain and forward transfer parameter in this case. We have identified this as Y feedback earlier itself. So, this is the feedback resistance, this is the amplifier, this is the load. Okay. So, we have the output taken across this is the input and this is the output current. So, in this situation we take the Y parameters because the Y parameters of the amplifier add to the Y parameters of the feedback network, and I am now taking the composite Y parameter, which is very easy. When we define the Y parameter, output is shorted. So, this 20K comes in shunt with the input resistance of the amplifier, which is beta plus 1 times Re. So, Re, since it is 0.5 milliamperes, is going to be 50 ohms because of 0.5 milliamperes current. So, beta plus 1 times Re, beta is 200, okay. So, 200 into 50, 10K approximately, okay. So, we will actually modify this so that our answers become beta equal to 199. So, this is exactly equal to 200 into 50, so 10K. So, now we have Y parameter at the input. When this is shorted, 20K comes in shunt with 10K. This is the Yi of the composite structure. This is that of the amplifier, this is that of the feedback network. And the other parameter is when it is shorted, we have to find out, okay, because of applying voltage here, okay, Gm times Vi is the current in the collector, okay, Gm times Vi is the current in the collector, and that will be flowing through the short circuit. Apart from that, Vi by 20K also will be flowing. Vi by 20K will be flowing in the opposite direction. So, we have minus 1 by 20K here. Apart from that, we have Gm into Vi. Gm is nothing but roughly alpha over Re, that is 1 over Re is 50, okay. So that is 1 over 50, that means 1000 by 50 millisiemens. So both these things are expressed in terms of millisiemens, okay. So in fact we can remove this K and express this in millisiemens, right. So all these things are expressed in millisiemens, remove the K. So these two are over. Now we want from the output, you apply a voltage at the output, short the input and find out the other parameters, 2 parameters. So output admittance, okay, is going to be this 1 over 20 K will anyway come, okay. Then we have 1 over 10 K, 1 over 10 K, 2 over 10 K. So if you say millisiemens, so many millisiemens, 1 over 20 K, 1 over 10 K plus 1 over 10 K. So when I short this, at the output we have these. If we had been given the output admittance of the transistor, that also will get added to this. So this is the total output admittance under input being shorted. Now only this parameter, when I apply an output voltage with this shorted, the only reverse transmission is due to this 20 K. So minus 1 over 20 millisiemens. This is the only reverse transmission. So everywhere we have put this amplifier thing first, okay. Amplifier Y parameters, this is 0, okay. Forward reverse transmission for the amplifier is 0, and these are the feedback Y parameter, they are getting added. So now the composite Y parameter, therefore in this situation is 1 over 20 is really 1 over 10 is 2 over 20 plus 1 over 20, that means 3 over 20 millisiemens, right, minus 1 over 20 millisiemens, right. This is 20 minus 1 over 20, which is, how much is it? 19.95 millisiemens, right. So this is again 4 over 20 plus 1 over 20, that is 5 over 20 millisiemens, all expressed in terms of millisiemens. So this is the Y parameter of the composite network. So how do I find out the loop gain? Loop gain is equal to YR into YF. So 1 over 20 minus of that into 19.95, very nearly 1, of course, okay. 3 over 20 into 5 over 20. So this is the loop gain. How much is this? This comes out as, this is very nearly 1, 15, 400 by 15 roughly, okay, minus approximately 400 by 15. 26.6 6 or 7 or whatever it is. That is the loop gain. So, it is negative, indicating that it is negative feedback, it is much greater than 1. So, all these things are valid. So, good loop gain. Now, we want to convert this in order to find out the forward transfer parameter, input resistance and output resistance. We have to convert it into Z parameter. It is the Z parameter, okay, that is the idealized parameter, okay, for this kind of feedback structure. So, we have to obtain the Z parameter. So, this is easy, right. These are all millisiemens. So, actually speaking, we have everywhere this into 10 to the power minus 3 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 coming into picture. So, that parameter is going to be, okay, 5 by 20 into 10 to the power minus 3, okay, that is Zi, this divided by this into this plus this into this. Therefore, what is the delta y? That is delta y is equal to, okay, 5 by 20 into 3 by 20 into 10 to the power minus 6 plus, right, 19.95 by 20 into 10 to the power minus 6. So, basically effectively this one very nearly 1 into 10 to the power minus 6, and this will be 15 divided by 400 into 10 to the power minus 6, which is very nearly equal to, how much is it, 10 to the power minus 6 roughly, because this adds on to this. So, very nearly equal to 10 to the power minus 6. So, dividing by 10 to the power minus 6 now, is it clear? So, dividing by 10 to the power minus 6, we get the Zi. Zr is 3 by 20 into 10 to the power minus 3, this divided by again 10 to the power minus 6. Zf is minus 19.95 into 10 to the power minus 3 divided by 10 to the power minus 6, and finally Zf is 1 plus 1 by 20 to 10 to the power minus 3 by 10 to the power minus 6. So, out of this now what is asked is first the forward transfer parameter, that is straight away here, okay. So, the forward transfer parameter, forward transfer resistance now is equal to this. So, it is about minus 19.95 into 10 to the power 3. So, you can see this is very nearly equal to the 20 K that we have used. This was the feedback resistance 20 K, and ultimately the forward transfer parameter should be equal to minus 20 K. This is what we have surmised earlier. So, we are getting it as very nearly equal to minus 19.95. It is always very close to, okay, the feedback resistance in the case of Y feedback. Okay. Then the input loop gain is already evaluated, right. Input resistance this is nothing but 5 by 20 kilo ohms. This is 19.5 K. Right. So, this 5 by 20K, which is really speaking 5000 divided by 20, 250 ohms. So, input resistance is pretty low. See, it is a current controlled voltage source. Input resistance should go down and output resistance also should go down, right. So, let us see the output resistance. That is this. So, 3 by 20K, that is 3000 divided by 20 ohms, 150 ohms. So, you can see that the output resistance also is pretty low, 150 ohms. Output resistance is low, input resistance is low, and forward transfer resistance has become almost nearly the passive resistance of 20K. So, this is the way it is going towards its idealization. So, by using a single transistor, we have seen how this negative feedback network modifies its functions, so that we can realize a fairly good current controlled voltage source. We had earlier considered Y feedback in order to realize idealized current controlled voltage sources. Now, consider Z feedback applied to a single transistor. This is the single transistor amplifier. Since we are applying Z feedback and we are going to use Z parameter, we have to consider the RCE, the output resistance of the transistor, okay, as finite. We cannot consider it as infinite. This is important because we are considering open circuit parameters. RCE must be considered as finite. We cannot consider the current source as having infinite output resistance. So, we are now going to put in series with this input. This is going to be removed from ground, and we are going to put in series with that a resistance RE. This is the feedback resistance. So, this comes in series with the feedback voltage here. So, the Vi is from here to ground. Now, this earlier input comes in series with this output comes in series with this. Now, the composite Z parameter we have to write. This has to be written very carefully now. Composite Z parameter is that parameter when this is opened, open circuited. Find out, apply an input current and find out the output voltage. So, we will put down the equivalent circuit here as our original equivalent circuit RE. If this is II, then we have beta times II as the collector current, and shunting this we are assuming that there is an output impedance of RCE. So, this is the structure of equivalent circuit. So, for this now we have to establish the composite Z parameter. So, when this is opened, if II is applied, beta times II will flow like this and this will flow like this. Establish a voltage here, beta times II times RCE, plus in this direction, minus in this direction. So, the voltage that is established, open circuit voltage, is minus beta times RCE here, and since this II is flowing here, this also should be II because this is open circuited. Okay. There is a circulating current of beta times II in this, and therefore, when II is this, this is also II. Okay. So, the voltage here is II into RE. So, this is going to be a further additional voltage in series with this. So, output voltage is this plus this. This is minus beta times RCE times II, and this is II times RE. So, this is the effective ratio of output voltage to input current. This is the forward transfer parameter of the composite structure. Now, as far as the input impedance is concerned, Okay, if this is II, this is beta times II, this one is beta plus 1 times Re times II, and this is simply II plus Re. So, this is going to offer an impedance of Re. That is over as far as input impedance and forward transfer impedance is concerned is over. Now, make the output current 0, input current 0, and apply a voltage here, apply a current here. If this is 0 current, there is no current in this. If this is open circuited. So, when I apply a current here, this current will be forced to flow through this like this, and therefore, output impedance open circuit is Re plus RCE, simply series combination of that. And the voltage, input voltage for this current is going to be I naught into Re. So, this is going to be reverse transfer impedance is going to be Re. This is the input voltage, okay, for an input output current, okay, I naught. So, this is the composite Z parameter, okay, of this feedback structure, which is nothing but this. So, now we have to find out the loop gain, which is nothing but this into this divided by this into this. So, minus beta RCE, okay, plus Re into Re. For it to be negative, this should be dominant compared to this. This is always the case. RCE itself is very high, beta times RC is still higher. So, you can neglect this, okay, divided by beta plus 1 times Re plus capital Re, whole thing into Re plus RCE. Once again, how to neglect? This is large compared to this, neglect this. Re is small compared to RCE, neglect this. Here we cannot say anything about, this may be of the same order of magnitude. So, we get RCE getting cancelled with Re, and in effect we have the loop gain equal to minus beta divided by 1 plus Re by capital Re, okay, into beta plus 1. So, this is the loop gain, which is going to be much greater than 1, okay, as long as this factor is not too high. Re into beta plus 1 is going to be of the order of capital Re, and therefore, this is going to be of the order of beta by 2 or so, which is pretty high. So, we know that the loop gain is negative and is high. Then we can convert it into Y parameter. Okay, by finding out delta Z is equal to this into this minus this into this, that is beta plus 1 times Re plus Re into, I will neglect this, RCA, okay, plus Re, I will make it RC itself, plus beta RCA, I am neglecting this, right, into Re. So, this is the loop gain, that is delta Z, which involves the loop gain. So, this is the modification factor of all the parameters. So, let us now first find out the forward transfer admittance, which is going to be plus beta RCE divided by this becomes plus plus beta RCE minus RE, that minus RE is neglected, divided by this factor which is beta RCE capital RE, okay, plus RCE into RE, that can be again ignored compared to beta RCE RE, RCE RE, okay. So, plus RCE, okay, to beta plus 1 times RE. Okay. So, this again is negligible. So, we can see here that beta gets cancelled, RC gets cancelled. This is approaching a value of 1 over RE as expected. So, this part, that is the y f of the modified thing is approaching 1 over RE. So, it is nothing but a voltage controlled current source whose forward transfer parameter is simply 1 over RE. Right. Now, it has boosted up input impedance. Okay. You can find out that by getting the yi is going to be once again RE plus RCE, in which RE is going to be ignored, this divided by delta Z, in which beta RCE RE dominates. This is the dominant factor. Okay. So, this can be really ignored. This is very nearly equal to delta Z is very nearly equal to beta RCE RE. So, beta RCE RE you can see here, right, yi is 1 over beta times RE, or Zi of this network is known to be beta times RE approximately. So, you can see that the input impedance is increased, output impedance also is increased. So, that is this RE plus RE into beta plus 1 divided by, this is output conductance, that divided by beta RCE RE. So, actually speaking, right, you can say that this is beta RCE RE divided by output impedance, okay, divided by RE plus RE into beta plus 1. So, you can see that it is nothing but, okay, beta RE to RCE. Right. So, you can just divide this by this. We had already considered as loop gain, beta divided by 1 plus RE by capital RE into beta plus 1, okay, is the loop gain. So, original RCE gets multiplied by this loop gain, that is the output impedance. So, you can see that almost every way it is going towards voltage controlled current source idealization. So, this is a very simple negative feedback circuit. Okay. This is also can be thought of as, this also can be thought of as a situation where emitter bypass capacitor has been removed and consequently it gives feedback. Okay. In our earlier common emitter amplifier, assume that emitter bypass capacitor has been removed, then what happens? This is what happens. This we have illustrated in the lab experiment by removing this capacitor and showing that the amplifier becomes linear, input impedance increases, output impedance increases. Now that you have understood thoroughly single transistor Z feedback and Y feedback arrangements, I would like to discuss the very fundamental concepts about negative feedback using a single transistor where no passive network comes into picture. That is total negative feedback. Okay? Total negative feedback of voltage or current. What happens? This is interesting part. Consider the single transistor circuit. This is the input terminal. Normally output is taken there, right? There is no reason why output should be taken there. You can also take it at the emitter itself. But I would like to now see that if this is Vi, okay, Gm times Vi is the output current. But that output current is also available here almost nearly at this point. Please note that. And I want to give complete feedback of the output voltage. That means output voltage, if it is going to be taken here, suppose let us say output voltage is taken here, right? This output voltage is fed back to the input. This is the amplifier, okay, input terminal. Okay. This is the actual input before feedback. This is grounded. So, this input was directly getting applied to base and emitter junction. Now, base emitter junction comes in series with the actual output voltage. So, I can take the output as well at this point because Gm times VBE is also available as current here, okay, instead of. So, I connect this to ground and take the output voltage here. So, now this input voltage minus this output voltage is this, okay, input. So, this is exactly what we had considered earlier. This is my amplifier, okay. I do not have any feedback factor here, no passive network is being used, output voltage is completely fed back to the input. So, this is Vi minus V naught, okay. This is amplified as A times Vi minus V naught. So, what happens to V naught over Vi? In this total feedback arrangement, okay, this G is equal to A. So, you get, if A is very high, this becomes 1. Okay. So, the basic concept of feedback network, we have put an amplifier with the gain G that is equal to A in this case, and there is an error, okay, detector here which will just take Vi minus V naught and apply it to the input. This is Vi, this is V naught, okay. Vi minus V naught is what is applied to the input terminals of an amplifier, okay. So, this Vi minus V naught is really the VBE, Gm times that, okay, Gm times VBE, which is nothing but Vi minus V naught is the output current, that is the collector current, okay. Emitter current is alpha times higher than that, that is the current that is flowing 1 over alpha times that. So, that is the current that is flowing here, okay. So, if you have a resistance here as RL, which is normally put as RE, let us say, okay. So, this current is going to flow through RL and that will be the output voltage. So, what is the A factor? Nothing but Gm RL by alpha in this case. The same thing Gm RL, which is nothing but Gm RE in this case. RL is same as RE, okay. So, I am putting a load which is called RE. So, gain is Gm into RE instead of RL, okay. RL equal to RE. Right. So, the gain A factor is nothing but Gm RE by alpha, okay. So, what is V naught over Vi is going to be nothing but A by 1 plus A, which is Re Gm by alpha divided by 1 plus Re Gm divided by alpha, okay. Or this can be rewritten as 1 by 1 plus divide this whole thing by this factor, alpha divided by Gm into R. Alpha is very nearly equal to 1, Gm into Re is a huge value supposedly, and therefore, this is going to be very nearly equal to 1. This is called common collector amplifier, because the earth is common to input and output, okay, and that is grounded here. Emitter is not grounded. Emitter is the point where the output voltage is taken. So, this is the case of total negative feedback as far as the output voltage is concerned, right. No feedback network is used, right. So, you can see that this is the gain of the circuit, which is very nearly unity gain. This is also called voltage follower. Output voltage will be following the input voltage always, and since this output voltage is fed back to the input it is coming in series with the original input. So, input impedance is increased, it is the output voltage which is sensed, and therefore, output impedance will come down. Okay. So, this is an idealization towards voltage controlled voltage source. Ideal voltage controlled voltage source, okay, unity gain with feedback, okay, this gain is going to be very close to unity irrespective of the load resistance that you use. Okay. So, this is a common buffer stage used between source and another amplifier, so that the loading of the source, okay, does not occur by the amplifier. So, this is used commonly as a voltage buffer, right. Similar to this could be a situation of total negative feedback, which is current, right. That also we have to see. Let us now consider that. So, again if I give total current negative feedback, the current gain has to become close to 1, like voltage gain becoming close to 1. Let us consider this amplifier of ours. This is the input current, this is the output current. What is I naught by II? This is equal to beta, already defined. Okay. This is the short circuit current gain beta if I short this. So, this is a current amplifier. So, now let us suppose give current feedback. What will I do? I will give this total current as feedback at this point. Now, that is a very easy thing I told you, current feedback. This was originally II, and at this point now you will get the error current, which is nothing but II minus I naught, right, because this is I naught. So, I naught is flowing like this. So, this current base current is II minus I naught. So, now this does the current feedback, it is shunt, okay. Instead of in series, now the current feedback is always in shunt with the original current. Okay. So, I naught II minus I naught is the error current. This into beta is equal to I naught. That means I naught by II is equal to beta divided by beta plus 1, or 1 by 1 plus 1 over beta, which is very close to 1, which is actually speaking equal to alpha, right. So, you can see this structure, if you consider only in terms of currents, this is the input terminal for the current, okay, this is the output terminal for the current. What is common to this, you can put a load here also, no problem. Okay? That does not affect it at all, right? The current feedback is still. So, this is the output terminal for the current, this is the input terminal for the current. What is common to it is nothing but the base, right? You need, so this is common to this. This is therefore called common base amplifier. The earlier one was common collector amplifier. This is one with total current feedback from common emitter amplifier. This is called common base amplifier. The current gain from here to here now is going to be alpha, okay? Because this is emitter current, that you know anyway. This structure now becomes automatically common base, because actual input current is nothing but the emitter current, and therefore, this is common base amplifier. Okay? So, what happens? Input impedance comes down because it is shunt at the input, output impedance goes up by a factor corresponding to loop gain. What is the loop gain? Beta. Okay? So, if earlier output impedance is RCE, okay, the present output impedance is beta times RCE. Okay? If earlier input impedance is RE into beta plus beta, the present output impedance is RC, that is RE into beta divided by beta RE. Okay? And the gain is also modified by loop gain plus 1, beta by beta plus 1. So, these are the fundamental issues involved. So, this is an idealized current controlled current source. Okay. So, you have now seen using a single transistor without using any feedback network, by giving total voltage feedback, we have realized a common collector amplifier which is called voltage follower. This we have realized a common base amplifier which is called a current follower, you can call it, okay, or it can be used for current buffer stages. Instead of voltage buffer stages, you can have current buffer stages, right. So, current control current source with unity gain. Okay. So, these are therefore also called wideband structures. The common collector and common base structures will have a bandwidth which is going to be again loop gain times higher than the common emitter amplifier bandwidth, respectively for voltage gain in the case of common collector, current gain for common base. It is the current gain whose bandwidth is improved by a factor of beta plus 1 in the case of common base structure. It is the voltage gain whose bandwidth is improved by a factor of beta plus 1 in the case of common collector stage. Okay. So, this is the basis of the basic amplifier stages. The fundamental amplifier which we had considered earlier is the common emitter amplifier, and negative feedback configurations are common collector and common base respectively, with total voltage and total current negative feedback. So, we will consider double transistor stages or transistor pairs for negative feedback amplifiers in the next class. We will note that using feedback networks, it is not possible to get H and G negative feedback structures with single transistor. Of course, if you consider these basic stages, they are H and G feedback structures, but these are not using additional feedback network for the feedback. If you want to use additional feedback network, passive networks, and these passive networks are to be becoming effective, then there is no possibility of giving negative feedback with H and G. We will see that H and G become negative feedback only when we use a pair, and in the case of a pair, you cannot get Y and Z as negative feedback. If you want Y and Z as negative feedback, you have to use a treble, right. So, this is the fundamental issue of negative feedback. Okay. If you use y and z with pair, you will come up with only positive feedback structures. The loop gain will be positive. This you can actually work out and see for yourself by evaluating the loop gain by the method that we have followed. So, please see that if you use a pair, y and z feedback will be automatically positive. A pair can only have h and g as negative feedback, so on and so forth. So, the odd number of stages will always be suitable for y and z feedback, even number of stages are always suitable for h and g negative feedback structures.